Hello GATE aspirants, welcome to part 8 of GATE Thermal and Statistical Physics series. Question number 9. Consider a triatomic molecule of the shape shown in figure below in 3 dimensions. The heat capacity of this molecule at high temperature much higher than vibrational and rotational energy scales of the molecules, but lower than its bond dissociation energies are. So for this, first of all, let us calculate degrees of freedom. We have first translational degree of freedom, which is equal to 3. Then we have rotational degrees of freedom. This is a non-linear molecule, so rotational degrees of freedom is 3. If it was linear molecule, then it will be 2. Next is vibrational degree of freedom. This is equal to 3n minus 6 if this molecule is non-linear. So number of molecules is 3. So 3 into 3 minus 6. So this is equal to 3. Now total energy is equal to, for translational and rotational we multiply by half kBt, and for vibrational kBt. So this will be 3 by 2 kBt plus 3 by 2 kBt plus 3 kBt. This is equal to 6 kBt. So heat capacity is equal to du by dt, which is equal to 6 kV. So option D is correct here. Next question. A reversible Carnot engine is operated between temperatures T1 and T2. T2 is greater than T1 with a photon gas as the working substance. The efficiency of the engine is. Efficiency of Carnot engine is 1 minus temperature of sink upon temperature of source. So that is equal to T1 by T2. So option B is correct. It does not depend on the working gas. Next. Water freezes at 0 degrees Celsius at absolute atmospheric pressure. The densities of water and ice at this temperature and pressure are 1000 and 334 respectively. The latent heat of fusion is given. The pressure required for depressing the melting temperature of ice by 10 degrees Celsius is. So for this we will use Clausius-Clapeyron equation. Which is dP by dt is equal to L upon T delta V. Now delta V here is volume of ice minus volume of water. So that is mass upon density of ice minus mass upon density of water. So here delta P is equal to L into delta T upon T into delta V. So this will be 3.34 into 10 raised to 5 into delta T is, it is depressing of melting temperature. So that means this will be minus 10 upon temperature, that is original melting point, that is 273 into we have 1 upon 934 minus 1 upon 1000. And after doing this calculation, you will get 0.17 gigapascal. And answer for this question in the answer key is 0.15 to 0.19. Next question. Consider n non-interacting distinguishable particles in a two-level system at temperature T. The energies of the two levels are 0 and E, where E is greater than 0. In the high temperature limit, kBT much greater than E, what is the population of particles in the level with energy E? So this is non-interacting and distinguishable particles. So this is Maxwell-Boltzmann distribution. And for this, Pi is equal to e raised to minus beta ER upon Z, where Z is partition function, which is equal to summation over I e raised to minus beta ER. Now, energy is 0, so first term is 1, then e raised to minus beta E. This is Z. Now in the question it is given that kBT is much greater than E. So here E upon beta kBT will be much smaller than 1. So we can write e raised to beta E is nearly equal to exponential series 1 minus beta E. Because this value is very small, higher terms can be neglected. So P of E, that will be equal to e raised to minus beta E upon 1 plus e raised to minus beta E. So this can be written as 1 minus beta E upon 1 plus 1 minus beta E. But beta E can be neglected as compared to 1. So this is like this, beta E. So this can be neglected. So this is equal to 1 by 2. And number of particles in that energy level will be total number into probability. So that is equal to n by 2. So here option A is correct. Next question. The energy density and pressure of a photon gas are given by U is equal to AT raised to 4 and P is equal to U by 3, where T is temperature and A is radiation constant. The entropy per unit volume is given by this expression. Now we know dQ is equal to TdS, which is equal to du plus Pd. Now entropy per unit volume, so let us differentiate this with respect to volume. So this will be T into, we have dou S by dou V, we'll do it at constant temperature. Then we have dou S by dou V at temperature T, and P dou V by V, so that will be 1. So from here dou S by dou V at constant T is equal to, here it will be dou U by dou V. Now this is energy per unit volume, so that is U here plus P upon this temperature T. Now here it is given that U is equal to AT raised to 4 and P is equal to AT raised to 4 by 3 upon T. So this is 1 by T into 1 minus 1 by 3 is, 1 plus 1 by 3 is 4 by 3 AT raised to 4, so that is 4 by 3A T cube. So by comparison we see that alpha is equal to 4 by 3, which is equal to 1.33. So answer is 1.33 and answer in the answer key is 1.30 to 1.36. Next question. Consider two particles and two non-degenerate quantum levels 1 and 2. Level 1 always contains a particle. Hence, what is the probability that level 2 also contains a particle for each of the two cases? When the two particles are distinguishable and when the two particles are boson. So first case is when the particles are distinguishable. In that case, let those two particles be A and B. So this lower level always contains a particle. So this can have AB or AB. So in the upper level it will be B, A, and here it will be 0. So probability that there will be particle in upper level is 2 by 3. And second case is indistinguishable particles, that is bosons. So this particle is A or it can be A. So in the upper level it will be A or 0. So probability is equal to half. So here option C is correct. So these were all the questions from GATE 2017 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.